Well, we introduced you to the second fundamental theorem of calculus last night just so we could set the stage for tackling some accumulation functions tonight, and they're very closely associated with the second fundamental theorem, and you're going to feel yourself using that theorem over and over tonight. Now, basically, our definition for an accumulation function is a function that is defined in terms of an integral. And it's going to take us a little while to get used to this idea that of a function being defined in terms of an integral. But we definitely saw some last night. Now, a definite integral is, I want you to, let's say it's as a function of x here, and let's say capital F of x equals the integral from a to x of little f of t dt. Alright, so let's analyze this setup. What we've presented you with is an example of an accumulation function. Specifically, the capital F is the function that's considered the accumulation function. Alright, and let's see, what do we got cooking here? The lower bound, right here, let's just make a note that the lower bound has to be a constant. It's kind of like acts like a starting line for us. The upper bound has to be a function of x. In this case, it's just in most cases tonight, it's just going to be simply an x. It won't be anything other than that. And then we have the function that's being integrated there, and you'll notice that little f is a function of t, and we just made sure that this variable differs from the variables that we're using right here. Now, they won't always use a capital F of x. In fact, most of the times on the AP exam, they're going to use something like the lowercase g of x. And we've got an integral from a to x of f of t dt. So the lower bound might be a 0, might be a 1, might be a -2, it might be a 4, anything like that, and the upper bounds are x. So g is called an accumulation function, and I think that name will make more sense once we start getting into some live examples, but I just want to go over some basics today. If you see a question when they ask you where g of x is increasing or decreasing, you're instantly going to go to g prime. And here's where your second fundamental theorem comes into play. If you want to derive this expression up here, if we want to take his derivative, let's just say we're going to derive both sides, that's where your second fundamental theorem kicks in. We need to do f of u, which in this case is f of x, times du, which luckily is just a 1. So all we're really saying is that g prime of x equals f of x. Again, if they want to know where g has any relative maxes or mins, again, we're going to take a look at g prime, which is actually f, and we're going to figure out where he changes from positive to negative. If they want to know when g is concave up or down, we're going to go to his second derivative, which in this case is simply the first derivative of f. And again, the same thing for points of inflection. We're going to go analyze g double prime, which is one and the same thing with f prime. So I've imported a very nice, well-behaved graph here, and this is the graph of little f of t, and I'm going to introduce you to an accumulation function. Let's see, g of x is defined as the integral from 0 to x of f of t dt. Whoops, that's got to be a t. I almost screwed that up. Okay, so let me grab my eraser and see if I can clean this up at all. Alright, so it's got to be a t. Alright, so g is an accumulation function, and I think it makes sense because you're starting at 0, and let's see, as we sweep from left to right, we are accumulating chunks of area. And basically, g is going to keep a running total of how much area has been accumulated as we sweep from left to right, and so forth. Notice he does continuously add positive chunks of area up until we get to 4. So we're going to say g reaches its maximum value at 4, because once I pass the 4, I start to add negative chunks to my total, thus decreasing the overall net gain that I've accumulated. So we'll go ahead and we'll jump in. Let's pose this question here. When is g increasing? Question mark. All right. Well, I'm going to say to myself, whenever g prime is positive, that's my first thought. So, and we know by using the second fundamental theorem, we know that g prime of x is equal to f of x. And we'll notice we make a little sign chart here. There's a critical point at 0. There's a critical point at 4. There's a critical point at 8. And on my sign chart, I like to label it g prime slash f, just to emphasize that they're one and the same. And I would say that f's all positive up until from 0 to 4, because everything here is above. and then it's negative afterwards. And so we know that g is increasing from 0 to 4 and then decreasing thereafter. So we can successfully answer our question 0 to 4 because g prime slash f is positive. All right, here's our first mega problem for the night. And they said the graph of f shown below consists of 5 different line segments and a semicircle, and g is defined as the integral from 1 to x. Now, just because the integral is not a 0, or the lower bound is not a 0, we're still okay as long as it's a constant. So they want to know, they've got 3 questions here in part A. So when they said g of 5, and I'm hopefully going to be able to fit this in here, they want me to substitute a 5 in for x, and that became the integral from 1 to 5 of f of t dt. So what we're doing is we're saying, okay, from 1 until I hit 5, I need to figure out how much area has been accumulated. So I'm going to do from 1 to 3 is a nice triangle. Looks like we've got a base of 2 and a height of 4, so that's an area of 4. Plus, now I've got a very odd shape here. What I'm going to do is I'm going to find the area of this rectangle, which looks like it is, let's see, 2 by 4 is 8. And then what I'm going to do is I'm going to subtract the quarter circle away from it, so that'll leave me with the space underneath the curve. So the quarter circle looks like it's got a radius of 2, 1/4 pi r squared. Looks like it's just going to be pi. So 4 plus 8 is 12. I'm thinking 12 minus pi is the g of 5 value. Now, before I do g prime of 5, I'm going to say, well, just remind myself that g prime of x is really f of x. So g prime of 5 is really f of 5. And I know that f of 5, this is the easier one, is just, we're going to just read the curve right here, and we're going to say f of 5 equals 2. Alright, the last one is g double prime of 5. Now we know that g double prime of x equals f prime. And so what I'm going to do is I'm going to go to the 5, I'm going to read my slope, and because it's a relative min, we've got a slope of 0. So I'm going to say g double prime of 5 equals 0. Alright, let's see if I can squeeze in part B here. G of 1. G of 1, they want me to substitute a 1 in for x. The integral from 1 to 1 of f of t. I love it. The bounds are the same, so we've accumulated 0 area. G prime of 1 is going to be the same thing as f of 1, which, oops, got an x-intercept there, so that's also 0. G double prime of 1 is going to be the same as f prime of 1. So I'm going to go read the slope, and it looks like I've got a line segment with a slope of 2. So g double prime of 1 equals 2. Let's see. Part C. Find all values of x on the open interval negative 8 to 8 for which g attains a relative min. Now what you want to continuously tell yourself is, this is, yes, this is a picture of f that I'm staring at, but it's also a picture of g prime, because g prime and f are one and the same. And so I want to know, in order for g to attain a relative min, we know that g prime has got to do what? He's got to change from negative to positive. And at what point does that happen? I would say right at x equals 1, and so I'm going to say at x equals 1, g has a relative min, because that's when g prime slash f change from negative to positive. Part D is a little more involved. They want to know when we reached our absolute maximum value of g, and what we're going to do is we're going to make we're going to use the closed interval test. We're going to make a table of values. We're going to include our endpoints, negative 8. We're going to include any critical points, such as negative 7. I'm going to have to make a couple of tables here to fit them in. Let's see, we're going to use 1 as a critical point, and then my other endpoint was 8. And I'm going to be plugging these all into g, just to clarify which function we're plugging into here. Alright, I just cut away for a second. I kind of created a new slide here so I had more room to, do my work as neat as I can. Alright, we said the critical point, or endpoints, negative 8, critical point, negative 7, critical point of 1, and endpoint of positive 8. What I'm going to do up here is I'm going to go up to my graph and I'm going to break it into nice geometric shapes and just calculate the areas as I go across. So as I broke those regions up, I came up with an area of 1, an area of negative 3, area of negative 8, an area of negative 1, an area of 4, and then I did a rectangle that was up here at 16, and I subtracted the semicircle away, and what I was left with was the area, and then the last triangle had an area of 2. So that's going to help me figure out these values. So let's see what we got cooking here. When I said g of negative 8, I'm going to substitute negative 8 into the upper bound. And I don't really like it like that, so what I'm going to do is I'm going to switch the bounds and negate my integral. And how much area have I accumulated from negative 8 to 1? Well, let's see. Starting at negative 8 here, I've got 1 minus 3 is negative 2, minus 8 is negative 10, minus 1 would be negative, let's see, negative 11, and then plus 4 would be 7. Whoops, I went too far. I want to stop right at 1. So that should be a grand total of negative 11. Alright, when we do g of negative 7, I'm going to substitute negative 7 into the upper bound, but then I'm going to switch them again. I'm going to go from negative 7 to 1, and that's going to give me negative 12. If I do g of 1, we already did that one earlier. The integral from 1 to 1 is simply 0. And then if we want to figure out g of 8, we've got to do the integral from 1 to 8, and that's how much area is that. Let's see, starting at 1, I've got a 4 plus the 16 minus 2 pi plus the 2. I think that's going to be 22 minus 2 pi. So let's make sure we answer the question correctly. Find the absolute maximum value of g. I would say the absolute maximum value is 22 minus 2 pi. Alright, part E is the last part for this particular function. And just to recall, we've already g of x is the integral from 1 to x. So as soon as they mentioned point of inflection, I started, a little voice in the back of my head started screaming second derivative. So we know g prime is equal to f of x, and therefore g double prime is really f prime of x. So a point of inflection means f double prime, or I should say g double prime's got to change signs. So I'm going to attempt to make a sign chart here. My sign chart is, I'm going to use g double prime slash f prime, just to emphasize that they are one and the same thing. I kind of have a critical point there at negative 7, but I'll put it on here just to be safe. I've got a critical point at negative 4. I've got another critical point at 0. Let's see, I've got a critical point at 3, at 5, whoops, right there, and 7. So let's see if we can squeeze 3 and 5 and 7 on there. Alright. Extend my number line just a little bit. See if I can move this slide over a little bit. Alright. Okay, so now remember, when I say f prime, I'm referring to the slope of f. So I've got to go to this graph, and I've got a whole bunch of negative slopes, negative, 0, positive, negative, positive, negative. And those are the values that I'm going to put in my sign chart. So I've got some negatives, some more negatives. I got a bunch of zeros. That's kind of weird. From 0 to 3, we're all positive. 3 to 5, they're negative again. 5 to 7 is positive, and then 7 to 8 is negative. So I'm going to say there's a point of inflection at, let's say, 3, 5, and 7. I'm going to say points of inflection at x equals 3, 5, and 7, because, why? G double prime slash f prime changed signs. Let's put a big old exclamation on that. That's the last one for that problem. Alright, I'm going to introduce you to a new accumulation function up here. H of x is defined as the integral from 0 to x of f of t, which is the picture we have right here. So we're staring at a picture of f. And real quickly, we could say that h prime is, using our second fundamental theorem, is f of x times 1. H double prime is equal to f prime. And that's going to guide us throughout the entire problem. So when they said h of 2, let's see, h of 2 is going to be the integral from 0 to 2 of f of x, or I should say f of t. Got to be careful here. So from 0 to 2, we've got some area in there. It's going to be below the x-axis, so it's definitely negative. I believe that triangle has an area of negative 3 units. When they said h prime of 2, I'm thinking f of 2, which means I just read the graph, value is 0. H double prime of 2 is really f prime of 2, which means I'm going to go look at the graph. I'm going to read his slope. I'm going to say it doesn't exist because the function's non-differentiable. Alright, part B. They want to know on what open intervals is h decreasing. So I want to know when is h prime, well I already know h prime equals f. I want to know when are those functions negative, right? So I'm going to say, well, I'm going to make a sign chart. I know that f equals 0 at negative 2 and positive 2. Those are my critical points. Positive 2, alright. So we are above, and then we're below, below, and then above. So I'm going to fill in positives, I've got negatives, and then positives. And of course those are values of h prime slash f, which means h is increasing, decreasing, and then increasing. So the answer to this question, we're going to say h is decreasing from negative 2 to 2 because h prime slash f is negative. Easy as pie, huh? Alright, they want to know part C, when's h concave down? So I know h double prime equals f prime, and as soon as they said concave down, I wanted those functions to be negative. So again, when I say f prime, I'm reading the slope of this picture up here, and I believe the slopes are negative, negative, and then positive, positive. So technically my sign chart is going to have 3 critical points where the derivative doesn't exist. Negative 2, 0, and positive 2. But the signs are going to be, like we said, negative, negative, and then positive, positive. So we got negative, negative, positive, positive. So I'm going to say, and just to tidy up my sign chart, this was h double prime slash f prime, which meant h was concave down, concave down, concave up, concave up. Let's say concave down. We could say negative infinity to negative 2, union negative 2 to 0, because h double prime slash f prime was negative. Boom. Alright, part D's got a little trick in it. They want us to actually sketch the graph of f, which is kind of a daunting task. When in doubt, I like to construct a table of values, and what I'm going to do is I'm going to plug a bunch of these values in. Now remember, h is the integral from 0 to x. I'm going to plug in some of my favorite points and just get some idea of like some ordered pairs that fall on the graph of h. For instance, I'm going to start with, say, 0. The integral from 0 to 0 is 0, so there's a very nice point. 2 is also interesting. The integral from 0 to 2 gives you, let's see, I think that triangle right there is negative 3. And then this triangle up here is 1, so if I did the integral from 0 to 4, I'd get negative 3 plus 1, which is negative 2. So I'm going to go ahead, I'm going to put those points over here. I know the graph's got to go through 0, 0, 2 comma negative 3, 3 comma negative 2. Maybe we'll work backwards. Maybe I'll try negative 2. Now the integral from 0 to negative 2 is got to get flipped. So I'll do all the area from negative 2 to 0, which is negative 3, and then there's a negative on the outside, so I get positive 3. So negative 2 comma positive 3 right there on the graph. Negative 4, I'm going to try to fit it in. 0 to negative 4 is, I got to flip and negate. So I'm doing the integral from negative 4 all the way to 0. So if I add these two regions, I get negative 2, but there was already a negative weighting, so now I'm positive 2, and my graph goes right there. Now also pay attention to your part A answer and your part B answer. We know we've got to be concave down. We have a point of inflection at 0 because of the sign chart we made. Now we're going to be concave up, and the graph should look something like that. Whoops, I'm sorry. My 4 should be over here, so let's make... boom, maybe a little something like that. And I tell you what, part E is crazy. It's got some very thought-provoking questions in it. So they said, suppose f is defined for all real numbers, even though our picture only goes to 4 right here, to pretend that it continued to go on forever. And it's periodic with a period of length 8. In other words, every 8 units is going to repeat itself. Negative 4 to 4 is one cycle. 4 to 12 would be another cycle where this image just repeated itself. So the function would kind of go like this, and then down, and then up, and then slightly up. And then, from 12 to 20 would be another cycle. From 20 to 28 would be a cycle, so on and so forth. So what they want to know is they want us to see if we can figure out what the value of h of 12 is. Then we're going to try to write an equation for the line tangent to the graph of h at x equals 85. So that's a whole nother ballgame. Let's just focus on h of 12. So here's how I approached h of 12. I knew that h of 12, by definition, was the integral from 0 to 12 of f of t. And just keep reminding yourself that the picture we have right here, this is f of t. So I've got to find out how much area is bounded by that curve from 0 to 12. Now, the other thing I did is I kind of broke that integral into, I said 0 to 12 is really 0 to 4 plus the integral from 4 to 12. Alright? And we already know that from 0 to 4, let's see, we got a negative 3 plus a 1, that was negative 2. Now to go from 4 to 12, it's a whole nother complete cycle. It's going to be the same graph that we got right here, it's just going to be one more cycle. Now within one cycle, I said the combined area within one cycle was, let's see, how about negative 6 plus 2 would be negative 4. So I'm going to say that h of 12 is really negative 6. And that's how much area I would have, if I had the luxury of having the entire graph in front of me from 0 to 12. Alright, moving on to the second part, they want the equation of a line tangent to the graph of h at x equals 85. Now I need two key ingredients. I need h of 85. That's going to be my y value, or my y coordinate. I also need h prime of 85. And that's going to give me my slope. If I can get my hands on those two things, I'm going to be all good to go, and I'm going to be able to write the equation of my line. Now the trick is, if I could extend the x-axis all the way to 85, I need to know how many complete cycles are there, and then what partial cycle is at the end. Now, unfortunately, we can't extend our x-axis all the way to 85, but what I'm going to do is I'm going to help you try to visualize what you would see if the x-axis went all the way to 85. So what we've got cooking here is this big old number line. We'll pretend that 85 is on the far right. So from 0 to 4, we see half of a cycle. Alright, then from 4 to 12, we see another cycle. From 12 to 20. From 20 to 28, and I know this is a slow process and you're probably laughing at me, but I think it's going to be the best way to visualize what's happening to this function. From 44 to 52 is another cycle, from 52 to 60, from 60 to 68, from 68 to, let's see, 76, and from 76 to 84. Those are all complete cycles. And then from 84 to 85, we're going to just see basically what's equivalent from negative 4 to negative 3. A little just dab hanging at the end. So h of 85 is really the integral from 0 to 85. So what we've got to do is we've got to count up how much area have we accumulated. Now we know that every individual cycle accumulates negative 4 units of area. So let's see, I had a negative 2 from 0 to 4, and then I've got, negative 4 there, negative 4 there, negative 4 there, yada, yada, yada. So I've got, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 full cycles. So that would be negative 40. Whoops, I should say, yeah. Plus this guy's negative 42, plus the little bit at the end right there. So it's negative 42 plus something. Now remember, what was left over was just from 84 to 85, which is the same thing as going from negative 4 to negative 3. So I got to figure out how much area is in there. Well, I used the old trapezoid formula to figure that out, and I got 3/4. So negative 42 plus 3/4, because it would be above the x-axis. Very interesting number. But I'm going to say negative 41.25 is my y value. Now the next thing, the slope's not as bad, because what we're going to do is we're just going to we're going to say h prime of 85 is just equal to f of 85. And if you just visualize that this section getting repeated over and over again, the 85 would fall right where the negative 3 is. And so that value right there is 1/2. Now again, I'm not reading the slope at that point, I'm just literally reading its y value, and that tells you f of 85, which is really h of 85. Let's put it all together now, and let's see, y plus 41.25, what a friendly number, huh? With equals a slope of 1/2, times the quantity x minus 85. So that was a pretty obnoxious problem. We have seen a couple similar to that on the AP exam where they've based the question off the periodic behavior of a graph, and we kind of have to predict and forecast what it would look like beyond what was given to us. So hope you're able to hang in there. Hope you can appreciate the use of the second fundamental theorem tonight, and we're going to become pretty good friends with these accumulation functions. So good luck, and we'll see you.